Hi guys. How's it going?
Happy Monday.
Yeah, happy Monday to you too. Let's let everybody get admitted into class here. How's that? And all right, you guys. So, do you guys have a good weekend? Thinking about it. Thanks. So did I. I just wanted to mention a quick thing before we go ahead and get started. I'm teaching a class, summer 1, which is May and June, essentially. It's Math 3081. It's a calculus-based probability and statistics class. It's a really interesting and fun class, and I think it's, if you're a science or engineering major for sure, that it's a required class. If you are able or you're interested in taking it, my class is at 9:50 in the morning, and I think it's till maybe 11:30. I can't remember. Anyway, that's summer 1. So if you guys, I think that the registration's open for that now. If you were interested in taking it, if you have it in your schedule, be happy to have you in class. Anyway, so put that up to the side. Wanted to mention I got your exams online. It looks like most people were able to upload it just fine. The exams, please be patient with me as I grade them. It takes about 6 times as long to grade them as it should. And I don't know why it's online, but all my colleagues were all talking about how it takes so long to grade things while they're online compared to when I have a piece of paper. So please be patient with me as I work my way through them. If you have any questions about the exam itself and you want to ask me, please feel free to come to office hours and we can talk about it there. Okay. And certainly after you get your exam back, I'll upload the graded exams to Canvas, so you guys will have them there. After you have them, please, come to office hours so we can talk about it there. Okay. All right, we're going to continue on with chapter 5. So we did chapter 5.1. As you know, there was an exam question like that. The rest of chapter 5 is all about different series types and how we talk about their convergence or divergence and their sums if it's applicable and possible. There's a page on the modules for last week, right up where I posted chapter 5.1. This is the blank table, okay, that you guys can print out if you want, or you can use it as a template to make your own. We're going to have a whole bunch of different series types that we have. We've got example series, convergence, conditions, divergence, and then some comments on them too. So it can help to have some kind of a place where you aggregate all of the different series types together into one spot so that you can take a look at it there. All right. So with that said, let's go ahead and get started on chapter 5. Oh, and then also I wanted to mention, I almost forgot, this Thursday, chapter 5.2 homework is due at midnight. Okay. Chapter 5.3, which will start on Wednesday, will be due next week. Okay. Also, this Thursday, we will have a quiz. It'll be on chapter 5.2. Okay, so keep that in mind. 5.2 homework and 5.2 on the quiz this Thursday. Okay, so coming up. So the stuff that we're going to do today, you guys will have to pass in and be quizzed on Thursday. So keep that in mind. Okay, so chapter 5.2. So 5.2 is called Theorems on Series. So chapter 5.1 was about theorems on sequences. And today, and for the rest of chapter 5, we're going to be talking about series. Okay, so let's talk about what's the difference between those two. So the first thing is, let's talk about sequences, which is chapter 5.1, versus series, which is chapter, and I'll just write 5 greater than or equal to 5.2. Okay, so let's do this. So sequences, like we talked about in chapter 5.1, sequences are, say, for example, I'll just do an example sequence, n+1. This is a list. A sequence is a list of numbers. The list of numbers follows some algorithm, right? Some formula that tells me how to each successive term in that sequence, how do those, how do they get derived? So it's a list. So when n is equal to 1, I'm looking at 1 all over 1 times 2, comma, 1 all over 2 times 3, comma, 1 all over 3 times 4, comma, and so on and so forth. It's just a list of numbers, right? So this looks like 1/2, 1/6, 1/12, and so on and so forth. Okay, it's just a list, right? And we would say, to talk about convergence, what do all these numbers, right? This is just a list of numbers. So what do these numbers do? Do these numbers just get bigger and bigger, or do these numbers kind of converge to a value? So to talk about convergence, we do a limit as n goes to infinity of our, whatever our algorithm is. Right, and then I use my whole limit idea, right? So as I do that, oops, sorry, as n goes to infinity, right, I've got 1 over infinity. So this is 1 over infinity is equal to 0. So this thing converges, the limit exists, and this converges to 0. So that means that all of these terms are going to get smaller and smaller and smaller and smaller until they're basically indistinguishable from 0. Okay, so they converge to 0. So that's our sequence. That's what we did. That's summarizing chapter 5.1, right? Now a series is different than a sequence, because a series is, we're going to take each of these terms and we're going to sum them up. Right, this is my summation. Okay, which is, I'll write it like a sub n, right? So I have my my algorithm, the same algorithm that we used. This means summation. So each of these terms gets added together instead of being just lumped together into a list. So because we're going to add, so this is like a sum of those numbers, right? So it looks like, so my sum n equals 1 to infinity, 1 over n times n+1 is going to look like, I'm going to go 1 all over 1 times 2 plus, look, 1 all over 2 times 3 plus 1 all over 3 times 4 plus so on and so forth. I'm adding them together, right? That's what the summation symbol means. This is 1/2 plus 1/6 plus 1/12 plus so on and so forth. I'm adding up a whole bunch of numbers, right? I'm going to go up to infinity. Okay, but the question is, can I actually sum these numbers up? How do I sum these numbers up? Right? I'll tell you, you don't know this yet, but this thing sums to 1. Okay, you don't know why yet. But I'm not just taking the limit. I can't take the limit just like however, because I'm talking about a sum. I'm adding all these numbers up. It's not a list of numbers. I'm adding the numbers up. So what's going to happen for the rest of chapter 5 is we're going to show in chapter 5 how we know this series right here, sums to 1, okay? And also how we know that it converges. If it doesn't converge, I can't find a sum, right? I mean, if the summation is gonna diverge, right? Diverges usually means it goes to infinity or negative infinity. If it diverges, no, there's no sum, right? Because I'm just adding up an infinity of terms. So it's basically the sum is infinite. So what we need to do is essentially, we're going to be learning different tests for different types of series. Okay, and these tests are going to be specific to a series type. So we're going to learn in chapter 5 to recognize how to recognize this series type versus that series type. What are the criteria for convergence or divergence? If it converges, does the series type have a sum that I can calculate? That's all the stuff that's going to go here, right? This is our cheat sheet, right? Our summation sheet that's going to help us kind of together so that we can remember it, and then help us remember all of these things. Okay. Anyway, so some of the stuff that we're going to do in our lecture examples, I've got my lecture examples page here. Some of the stuff we're going to do in our lecture examples is more like lecture notes, like example 1 and example 2. Those are kind of like lecture notes, but I wanted to put them into the lecture examples so that we had them in one spot. So it was kind of easy to keep track of. Okay. All right. So looking at my lecture examples page, how is that? Is it blurry? It's okay. So we've got this, we want to talk about how do we sum up an infinite series? What do we do for that? So this is a power series, right? So the Maclaurin series is a power series, meaning it's a polynomial, right? It's got something to a power. We're going to do it for sine of x. Now remember, sine of x, the Maclaurin for sine, is what we call a fundamental Maclaurin, which means that the polynomial, the Maclaurin polynomial for the sine of x is equal to its function, which means if you remember from chapter 4, it means that for all values of x, this polynomial is going to converge on the sine of x. Okay, it means our radius of convergence is infinite. Okay, all values of x will converge. And then we're going to compute the partial sums, S sub n, and we're going to use it to estimate sine of 1. Okay, all right, so let's remember. So the Maclaurin for sine of x, it's an odd function, so it's x. We've got odd powers. And so on and so forth. Okay, it's an odd function. Now remember, if I do sine of 1, this is in radians now, remember, this is 1 minus 1/3, 1 over 3 factorial. So this is like 1 cubed. I'll put the cubed really small because it's 1 cubed plus 1/5. Remember the fifth I'm putting really small, just so you can see I'm plugging it in. And so on and so forth. We're going to sum that up. We can't sum it up all the terms, right? Because it's got an infinite number of terms. So we're going to talk about partial sums. So S sub n. Okay, S sub n is our partial sum. So that means, remember from way back, we talked about partial sums back at the beginning of chapter 4. So this means we're going to sum of terms up to and including n. Okay, that's our, all right, so that's kind of like, I'm going to say S sub 1, right? And we're doing this for sine of 1. Okay, so that means I'm going to take my first term, my first 2 terms. So this is actually like, this isn't like nth order. This means like how many terms in my sum. So I've got the first term, second term, right? And this is, I'll just start doing it at 1 minus 1/6, which is equal to approximately 0.833. My third partial sum is 1 minus 1/3 plus 1, 5, I'm sorry, 3 factorial, 5 factorial, which is equal to 1/6 plus 5 factorial is 120. That's approximately equal to 0.8416. My 4 terms in here. Okay, so 1 minus 1/6 plus 120 minus 1 over 5,040. I have a factorial button on my calculator. It's under math, PRB, probability. So you can keep that in mind. This is approximately equal to 0.841468. How am I doing on the side of the screen there? Can you see that okay? There. Okay, good. Just making sure. Okay, and then we'll do the 5th. The more we do, right, the better our term is, the better our sum is. 1 minus. This is approximately equal to 0.8417. 0.09. Now, if I do this on my calculator is probably doing this too, but it's going out, you know, like 100 or 1,000 terms. So if I do sine of 1 by calculator is equal to 0.841470984. So we're not too far off, right? We're like right about here. We don't really went out to the 5th partial sum, so it's a pretty good approximation. Okay, so basically, right, we're looking at our partial sums. So when I think about my sine of 1, remember this is in radians, is equal to the limit as my number of partial sums gets bigger and bigger and bigger, right? So think about it, like the more terms I add in my partial sum, right, the better my approximation is going to be. Okay. Okay. For however many n's we want to do. So what this basically means is we need to think about, we're going to define the, the sum of an infinite series to be the limit of the partial sums. Okay, so keep that in mind. For my partial sums going, that gives me the sum. Okay, that's not the limit of my nth term, right? That's limit of our nth term is what we did in chapter 5.1. Okay, that's like just the limit of my a sub n. That doesn't tell me anything about the sum. Okay, that just says what's our nth term doing. That's our sequence. Okay, but now we want to talk about like what's our sum of this infinite series. So this is an infinite series. It's a collection of numbers essentially, right? When I want to evaluate my sine function. So I want my sum of my infinite series to be the limit of my partial sum. So where is this sum going to? Okay, I'll let you guys finish writing that and then we'll turn the page. Right, so here's example 2. So if we think about example 2, given the sequence, derive a general term and use that general term to describe an infinite series. So let's remember, I'm just going to do this, n equals 1 to infinity, a sub n equals a sub 1 plus a sub 2 plus a sub 3 plus, and so on and so forth up to infinity, right? This is a sub n is any sequence, right? It was odd numbers, it was 1 over even numbers, whatever. So now we're going to sum up all of those terms, right? So we have a sequence. This was chapter 5.1. Now we're going to add each of those terms in the sequence together. So part of what we're also learning to do is kind of pattern recognition. So I'm going to look at these here. I'm going to start thinking about what's my general term, and then how would I represent this as an infinite series, right? Infinite series meaning our sum. So I've got 1 over 3, 1 over 9, 1 over 27. It looks like, well, 3 times 3 is 9, 9 times 3 is 27, so it looks like I'm just doing powers of 3. So I'm going to say a sub n is 1 over 3 to the n. Okay, that's my general term. If I were to make an infinite series out of this, I would say n equals 1. It starts at 1, right? Because I start off with 1 over 3. It doesn't start at 0, because if it did, I would have a 1, comma. This goes up to infinity. A sub n, which is 1 over 3 to the n. So what this looks like is, I'm going to go 1 over 3 plus 1 over 9 plus 1 over 27 plus so on and so forth. 1 over 3 to the 1, 1 over 3 to the 2, 1 over 3 to the 3, 3 to the 4, so on and so forth. Okay, we're just summing it up, right? This is our sum. The series is our summation. 1 over 1, 1 over 4, 1 over 9, 1 over 16. Oh, 1, 4, 9, 16, those are all squares, right? Perfect squares. So I'm going to go, the ends may be 1 over n squared. And again, I'm going to start this, to put this as a the algorithm for my infinite series. I have to start at 1 this time, because if I started at 0, I would have a divide by 0 problem. A sub n equals, this is 1 over n squared. Okay, so this looks like 1 over 1 plus 1 over 4 plus 1 over 9 Plus 1 over 16 plus so on and so forth. Okay, we're just going to add all those terms together. These two are very specific series types. We're going to actually learn about them in chapter 5, and we can actually calculate their sum, okay, and then figure out what, or come up with an approximation of their sums, okay? Will you guys finish writing that, and then we'll take notes again. Okay. So let's talk about what it means to converge, for a series to converge. So we talk about convergence of an infinite series. Like, what does that mean? How are we going to detail that? So if we say an infinite series, which we can call n equals k some number up to infinity, a sub n, it converges to the sum if its partial sums converge to S. Okay, let's write it in math. We'll talk about what S is. So we'd say the limit as n goes to infinity of S sub n equals S. S is our sum. This S is our sum, where S is equal to the sum n equals k to infinity a sub n. Okay, these are two different pieces here. So the limit of our partial sums, right, is our sum of our series. This is the sum of the series. So it only converges. How do we know if it's going to converge? There are a whole bunch of series tests that we're going to do that's going to tell us about convergence, okay? But it will converge to the sum only if the limit of the partial sums is equal to the sum of our series. Okay, it doesn't tell you how to figure out the sum of the series, but that's part of what we're going to learn in this chapter. So let's write if the limit does not exist, then the infinite series diverges. Often when it diverges, it goes to infinity, minus infinity. That means our sum's probably infinite or minus infinite too, okay? Okay, so let's start talking about series types. Our first series type that we're going to talk about is called a telescoping series. Okay, our telescoping series, I'm going to write out what it looks like first, and then we'll put it together. So B1 minus B2 plus B2 minus B3 plus B3 minus B4, B5, and so on and so forth. So it's kind of like n equals 1 to infinity. I'm going to go, right, this is my parentheses. So this is each group here. So this is 1 over n minus 1 over, or something. I'm going to make it n plus 1. Say, for example, that's what this one looks like. We're going to do it. This is actually like our next example. Right, so I've got this summation. So I've got my first chunk. This is my first chunk here. This is my second round of my summation. Third round, fourth round, so on and so forth. The thing about a telescoping series is, look at B2 minus B2 plus B2, they cancel. Minus B3 plus B3, they cancel. Minus B4 plus B4, they cancel. This one's going to cancel too. So what's left, right? I've got B1, that's not canceling, okay? And then whatever I have as my very last term, it would be like, let's say I were to end at, 6. So I go plus B5 minus B6. So then B6, okay, is the one that's left over. It doesn't have anything to cancel with because we said let's stop right there, okay? So that first term is sort of the limit of our last term. So we're going to talk about, it's called the telescoping, because like, they had the telescopes that like you'd look through them like this, and then when you're done, you'd collapse them. So this is the collapsing, like all this stuff cancels out and I'm left with the first and the very last. Okay, so let's summarize that. So I'm going to say my nth partial sum S sub n equals B1 minus Bn plus 1. So my very first term minus my last term plus 1. Okay, so I end at the the 5th, but I've got the 5 plus 1, my 6th term, that doesn't cancel. This thing is going to converge if and only if, IFF means if and only if, Bn plus 1 approaches a finite number as n approaches infinity. So let's write that whole thing in math. So we say, so the series, if the series converges, this would be the limit as n goes to infinity, Bn plus 1 equals finite. It's some real finite number. So if the limit exists, it's equal to some finite number, then this thing's going to converge, right? And then we can say if it converges, if the series converges, we can calculate the sum. The sum is going to be equal to the first term minus the limit of this n plus first term, right? Because this is the thing that's going to decide whether or not it converges. Okay, this is like our last term. What does our last term head towards, right? Minus the very first term, which doesn't cancel out. Okay, so we can calculate the sum on a telescoping series if it, obviously, if it converges. I noticed there's a typo on example 3. I'll tell you what that typo is. Okay, so example 3, I've got what type of series is this? So get in the habit of identifying the series type, because that identifying the series type is going to tell you what series test to do. When you're on an exam for this class, midterm exam, final exam, you have to tell us what series test you are doing. Okay, if you just do stuff and you say converges, here's the sum, you're going to lose points. Okay, so you must tell us what series test you're doing. So get in the habit of identifying what series type it is. The typo comes from here. It should be 1 over n minus 1 over n plus 1. Right, if I kept it the way it was, I'd have a divide by 0 problem on the first round. Okay, so 1 over n plus 1. So let's go ahead and I'm going to enumerate out so you can see what this looks like. So when n is equal to 1, I'm going to go 1 minus 1 over 2, right? 1 over 1 minus 1 over 1 plus 1, plus my next round up on my summation. N equals 2, n equals 3, n equals 4, and so on and so forth. Okay, so what's happening, right? Let's remember we did this before. So this cancels, these cancel, right? And this one stays. That doesn't cancel out with anything, but all these other terms cancel out. So I'm going to think about it. So I'm going to go, so my first term, b sub 1 minus the limit as n goes to infinity, b sub n plus 1. So let's go ahead and plug that in. So this is s sub n equals my first term, 1 minus the limit as n goes to infinity of this here, 1 over n plus 1. Okay. So what happens here? So I've got, as n goes to infinity, this thing drops out to 0. You have to say this, right? This is 1 over infinity, so this becomes 0. So then our sum is equal to 1. So the series converges, and our sum is equal to 1. So when I add up all of these terms, it's going to equal to 1. Don't try to figure it out like 1 minus 1/2 plus, what is this again? What's this? Don't worry. Just look at it, recognize it as a telescoping series, and then process it that way. And I'm going to go like this. Series converges by telescoping series test. Okay, and I can calculate the sum. But I have to say, what do I have to say? I have to identify the test that I'm doing. I'm doing the telescoping series test. I have to work it through, do the whole thing. I have to state what my limits are equal to, right? This is equal to 1 minus 0, so it's equal to 1. That's a real number, right? So it converges because this is a finite number. The finite number is 0. Converges by the telescoping series test. My sum for this is 1 minus this limit. 1 minus 0 is equal to 1. What are the conditions of divergence for the telescoping series? Well, think about it, right? If this thing right here doesn't go to a finite number, it's going to diverge, right? My very first term minus the limit of infinity or oscillation or, different left and right values means that this limit doesn't, if this limit doesn't exist, I can't do this sum, right? So this limit here is going to determine whether or not the telescoping series is going to converge or diverge, right? So converges if this limit exists to a finite number, if it exists, right? If it does exist, then I can calculate this sum.
Why do you, excuse me, for this one, why do you do limit as n approaches infinity of n over 1 plus 1 instead of like the whole equation?
Yeah,
series.
so because I'm talking about my very first term, right? My very first term is this one, and my last term, like these, like look at what happens when I repeat. So this 1 over n stays the same, right? And
Yeah.
then this part is going to cancel out all of my terms, and this is the thing that gets left over, 1 over n plus 1. You can think about it as like if I think like if I combine these and I say, okay, I'm going to do n plus 1, 1 over n plus 1. If I were to substitute n plus 1, what I'm going to be left out with is 1 over n plus 1 in the end, because I'm going to be subtracting out. Everything else subtracts out except for this last bit right there.
All right. Okay. I see. That makes sense. Thank you.
Yeah, telescoping series. We have to recognize, we usually have, it's a summation, but within the summation, sometimes we've got like parentheses. It's nice to kind of see it that way. Within the summation, right, I have a subtraction, and the subtraction is important because I'm adding a difference, right? And then that subtraction means I have a repeated term, which then gets canceled out on every round of the summation. That's part of it. That's how it telescopes down to just that first term and that very, very last term. All right, our next series type is called a geometric series. Okay, so geometric series, let's I'll write it out like it goes like this. N equals 0 to infinity, a times r to the n. Okay, a is a scalar, so it looks like a, right, when r is 0, and n is 0, a times ar plus ar squared plus ar cubed plus so on and so forth. Okay, and then a can't be equal to 0. I mean, it's not like it's a divide by 0 problem, but it's just, it would be summing up zeros, right? 0 plus 0 plus 0. It's not really a series at all. It's just a number. So that isn't going to work. So the criteria to converge, goes like this. My absolute value of r here can be positive or negative, right? My absolute value of r has to be between 0 and 1, has to be a fraction between 0 and 1, okay? Now what that means is that's the absolute value. So it doesn't matter if r is negative or not, okay? If r is negative or positive, but the absolute value of it has to be between 0 and 1. That means that my each successive term is going to get smaller and smaller and smaller. So if it converges, right, and then, oh yeah, so let's write down our diverge. To diverge, right, we say the absolute value of r is greater than or equal to 1. Okay, if series converges, it sums to s equals, we're going to go like this, a all over 1 minus r. So here's our sum. We can calculate a sum on a geometric series very nicely. There's something to know. Okay, if it converges, it sums to this, but note the sum is calculated assuming that n starts at 0, right? So I start at n equals 0. But for it to be a valid series, n can really start at any number. It can start at 100, it can start at 1,000,000, even though 1,000,000 is pretty big, but like 1,000,000, the difference between 1,000,000 and infinity, we're going on to infinity here. So 1,000,000 is still really small compared to infinity. But the problem is that my sum is calculated assuming we've got all those terms starting back at 0. So if the series starts at a number other than 0, then to calculate the sum, we have to subtract off all of those terms that we're missing. You subtract missing terms from sum, because this is the sum starting at 0. So let's pretend, right? So if I go n equals 2 to infinity, ARN, let's say it converges. Okay, good, it converges. So then our sum is going to equal to a all over 1 minus r, just like we would normally, minus n equals 0. So ar to the 0 plus ar to the 1, right? Because I missed n equals 0, n equals 1, right? I'm missing those terms. And it should have started, my sum is assuming it starts at n equals 0. But we didn't. We started at 2. We're missing the 0th term and the first term. So I have to subtract out the 0th term and the first term from my total sum, okay? So the thing is, when you recognize a geometric series, when you're given one, you say, oh, this is a geometric series. I'm doing the geometric series test. It converges. Usually you'll be asked to calculate the sum. Okay, so the sum is going to equal 2, right? And now you calculate this, and you go back and you look at your summation. Does it start at 0? If it starts at 0, you're done. This is fine. If it starts at 1, you have to subtract off the 0th term. If it starts at 10, I have to subtract off 0 term, first term, second term, third term, all the way up to 9th term, right? So I have to subtract off all of those terms that were missing from my summation sign here. Okay, this doesn't affect whether or not it's going to converge, but it will affect the number of the sum. Okay. So keep that in mind, because we usually try to trick you on that. You'll see that like on a midterm or on a final exam, we'll have a geometric series somewhere. And then usually we slip in that the sum doesn't start at 0. Okay, you'll check it that it converges, but then you'll forget to subtract off that 0th term from your sum. All right, so let's go ahead and do some examples. So example 4, right? What type of series does a series converge? If yes, what is it converge to? So I've got n equals 0, 3 over 2 to the n. So the first thing I'm going to do is I'm going to rewrite it. I'm going to separate out my 3 times 1 all over 2 to the n, just so I can see it a little more clearly, which means, oh, it looks like a geometric series. So I'm going to do a geometric series test. Somewhere along the line, you have to say what test you're doing. You can do it at the beginning, or you can say it converges or diverges by whatever test, but you have to say it at some point in here. So I'm going to identify my a is equal to 3, my r is equal to 1/2, because this is 3 times 1/2 to the n is what we're looking at. Okay, so my r equals 1/2 to the n, so it's a positive 1/2. So I'm going to go like this: 0 is less than the absolute value of 1/2, which is less than 1. Check. Yes, therefore it converges. Okay, I have to show this, I have to show this, I have to show that. What series test I'm doing. Now, what does it converge to? Well, we're going to calculate the sum. Our sum is going to be a all over 1 minus r. So I'm going to plug things in. So that's going to be 3 all over 1 minus 1/2. Now, the sign doesn't matter because I'm taking the absolute value. Sign doesn't matter when I calculate out convergence, but it's going to matter when I calculate the sum, because my geometric series will allow me to have a negative 1/2, right? Be careful, because that'll affect my sum. 1 minus, it'll be minus and minus, right? If 1/2 was negative. So keep that in mind. Watch out for your sign. It's going to be, it'll change right there. So 3 over 1/2, this is equal to 6. Okay. So this is our sum. All right. I'll scroll up. We're going to tweak it just a little bit. So I've got 3/2. This is still a fraction, right? So this is still a geometric series. Okay, geometric series, which means, let me check my geometric series test. I'm going to go 0 is less than 3/2, which is less than 1. Oh, 3/2, that's 1.5. No. Therefore, this series diverges, right? Because my a is equal to 1, my r is equal to 3/2. Okay. Doesn't converge. It diverges by my geometric series test. Okay. All right, so let's talk about some properties here. Let's talk about some properties. So properties of an infinite series. So I'll say my sum of a sub n and my sum of b sub n are convergent series. This is shorthand, right? Because it's like n equals some number to infinity, you know, some algorithm. A sub n and b sub n are two different convergent series. Okay, A, B, and C are real numbers. Okay, and then we can say the sum, our series A sub n sums to A, and our B sub n sums to B. Okay, it's just some preliminary stuff. So then the following series converge to the following sums. The first one, n equals 1 to infinity c times a sub n. Okay, if a sub n sums up to a, and I've got this c, I'm going to add multiply c times every term. It's like I can factor out the c, do my sum, and then multiply it back. So c times a. Okay. A sub n, b sub n, I'm going to add or subtract my individual series. They start at the same thing. Okay. I'm going to distribute. You can think about this as distributing my a sub n and distribute my b sub n. Okay. This is a common problem that we do. So my a sub n sums up to a, and my b sub n sums up to b. So I'm just going to add or subtract their individual sums. This is a common thing that we do. We're gonna trick you. We're gonna combine different series types together, and you're gonna have to recognize, ooh, that's telescoping, that's geometric. I'm gonna break them apart, analyze them, right? As long as both pieces converge, I can calculate or approximate their sums and then add their sums together. Okay, that's what that's saying. This is a common thing. We'll do this like on an exam, especially. We'll throw in those problems. Okay. Okay. You guys got that? Okay. All right. So another test. This one I'm going to write out. This is called the Nth Term Test for Divergence. And I always write out Nth Term Test for Divergence. I always have to say in my mind, this is a test for divergence only. It doesn't tell me anything about convergence. It's just divergence. Okay, so we'll say if the nth term, right? So we take our algorithm, we take the limit, our nth term of a sub n does not converge to 0, then the series a sub n diverges. If I were to write it in math, I would say the limit as n goes to infinity, a sub n does not equal to 0, then a sub n diverges. This is it right here. It tells me only about divergence. It's a good first go-to, but it can be often inconclusive. Tells us nothing about convergence. So if it's equal to 0, I don't know, could converge, maybe not. Okay, if it's equal to 0, if it's inconclusive, right, if it's equal to 0 or whatever, then I have to use a different series test. Okay, that'll happen, right? Like your good first go-to is the nth term. Like if you can't quite recognize what is the series type, you do the nth term test. But it's equal to 0. All the nth term test tells me is if it diverges, and it only tells me if it diverges if it's something other than 0. Okay, but it doesn't tell me anything about convergence. So it's often inconclusive. Okay, so be very, very careful because it's not going to tell me anything about convergence. All right. Okay, so let's do some examples. Example 6. Okay, by which test are we doing? So it isn't geometric, it isn't telescoping, right? Those are the first 2 tests that I already have. We're going to talk at the end of chapter 5 when we already have like all these different tests, like sort of like a flow chart decision tree of like, you know, what kind of, when you see this kind of thing, what should you do? Maybe what kind of, you know, series tests you should do. Okay, so it's not telescoping, it's not geometric. So let's try the nth term test. Term test for divergence. Look, I'm going to write the whole thing out just to keep myself honest, right? So I'm going to say the limit as n goes to infinity of 2 to the n. What's that equal to? That's equal to infinity, right? It's going to get really big, 2 to the n. Okay, well, infinity is not equal to 0. Therefore, series diverges. Right? It doesn't tell me anything about convergence, but infinity is not equal to 0. So therefore, this thing diverges. We're summing up. It's going to go up to infinity. Okay. Next example. Example 7. All right. n factorial over 2n factorial plus 1. We actually already learned the ratio test. That's coming up in, I forget, chapter 5.4. I'm trying to remember. But normally when I see a factorial, I do a ratio test. But in this case, we can do it. We have a factorial over a factorial. So it's kind of like an exponent. So I'm going to take my limit as n goes to infinity of n factorial to n factorial plus 1. It's like highest degree terms, right? I have an n factorial over 2n factorial. This is going to go to 1/2. Okay, I have to ask myself, 1/2 is not equal to 0. So this diverges by nth term test for divergence. Okay, I have to write all this out. This is to get full credit, right? I have to say what tests I'm doing, right? I have to show the test, what it's equal to, what the criteria is for divergence or convergence, and what my conclusion is. Okay. To get full credit, you have to do that. Sometimes people leave out this and I have to take off a point, which, you know, is unnecessary because you know what you're doing it correctly. So make sure you tell us what's going on. Okay. All right. Example 8. Does the series converge or diverge by which test? Okay, so 1 over n. So I'm going to do this limit as n goes to infinity, 1 over n. Oh, it's equal to 0. Well, that doesn't really help me, right? It's inconclusive. This is my nth term test for divergence. It's inconclusive. I need to use another test. We're going to learn, this is actually a p-series. This one actually does diverge, but it diverges by a p-series test. But you don't know that yet. But this, by the nth term test for divergence, it's equal to 0, right? As n goes to infinity, this limit goes to 0. Well, the criteria for divergence is that it's not equal to 0, which means it's inconclusive. I can't say it's going to converge, right? Because it's just inconclusive. So the other test I'm going to do is actually a p-series test, which you guys don't know yet. Wait, I was example 6, not geometric.
Could you quickly show example 7 again?
Yeah, example 7. This one.
Yeah, thank you.
So we can talk about it. So let's if we talk about it. So give me just a second. So example 6. So let's do this by geometric series test. So right. So we'll do so geo series. So we'll say A equals 1 and then R equals 2. Right, 2 over 1. We'll call it like a fraction, right? So if it's going to be a geometric series, 0 is less than the absolute value of R, which is less than 1, to converge. Absolute value of R is greater than or equal to 1 to diverge, right? So if my R absolute value of 2 is greater than or equal to 1, so it diverges, right? So it diverges by the geometric series test. You can think of it as a geometric series. It's going to diverge by that as well. The nth term test, we're just trying to illustrate a different type of test that you can do. So, I mean, it's going to diverge, which we knew already from the nth term test, but it also, if you did it with the geometric series test, I would expect it to diverge as well, okay? But that's our criteria. So the nth term test, like I said, is a good first go-to test, but it is often inconclusive, okay? Which is why, like I'll do this often, like unless I recognize what type of a test that I need to do, I'll do this first. And then if I get something inconclusive, then I'll just go in and try some other test, okay? Inconclusive means something like we got on example 8, okay? Which is 1 over n. I take the limit as n goes to infinity, I get equal to 0. That's inconclusive by the nth term test. Okay, so we're going to learn this is this actually does diverge, but you don't know it yet. You don't know why. Okay. All right. So some notes just to kind of wrap things up. So, okay. So some things to think about. Don't confuse the limit of terms, which is our limit as n goes to infinity of a sub n, with the sum of the series. S is equal to the sum, right? My sum is, I'm summing up all of those a sub n terms. 1 plus 1/2 plus 1/3 plus 1/4, so on and so forth. The limit of 1 over n is going to be different, right? So the limit of my terms, be very careful that people get these confused, but they're very different ideas, right? We're talking about the limit of the terms versus the sum of the series. The terms are a sub n are what are being summed up. Okay, the terms, we're summing up our terms. The sum of the series is the limit of the partial sums. Kind of like our very first problem with the sign, okay? Okay, there's also something I want to talk about in terms of like, kind of like a concept, like logic. On this, you know, terms versus our sums. Okay, so in this vein. So I'm going to tell you this is incorrect. A couple of incorrect arguments that people make all the time that they do this. Okay, so they go like this. They say, let's sum up the terms. Sum equals 1/2 plus 1/4 plus 1/8 plus so on and so forth, right? So then that's my sum. I'm going to sum all those up. So then therefore 2 times the sum, I'm going to sum, look, I'm going to multiply 2 by all of these terms. So it's going to be 1 plus 1/2 plus 1/4 plus and so on and so forth, right? I did multiplied everything, right? So this is basically like 1, this whole thing is my sum originally. So this is like 1 plus my sum. So that's like saying 2 times the sum is equal to 1 plus the sum, right? So the sum is equal to 1. Okay, but that's wrong, okay? What I need to do here, this is incorrect. What I need to do is I have to identify the series type. Check to see if it converges, right? And if it converges, then use that series type to help me figure out what the sum is. Then with the series type, then find sum of that convergent series, if this series is going to converge. Okay, so be careful. You can't just kind of willy-nilly work with this. You got to identify what the series type is. We'll do it in a little bit more obvious way too. So here's the, I'm going to tell you ahead of time. Here's the divergent series. It's kind of more obvious. So if I say the sum is equal to 1 plus 2 plus 4 plus 8 plus 16 plus so on and so forth. I'm going to keep doubling my terms, right? My sum, adding up all of my terms. So if I go 2 times the sum, that's 2 plus 4 plus 8 plus 16 plus 32 plus, so on and so forth. We're just multiplying 2 by each and every term, right? Which is equal to our sum minus 1, right? Let's just subtract off my sum minus 1 from here, okay? Which is like saying 2s equals s minus 1 minus s minus s. So this becomes s equals a minus 1. So my sum is equal to minus 1, which is not true. Okay, it's pretty obvious. You can see it, right? 1, that's 3, 3 plus 4, the 7 plus 8. I mean, so you can see right away that my sum is not equal to minus 1. I don't even have any negative terms in here at all. Okay, so you can't be working erroneously like this and making these erroneous assumptions. Okay, you have to be looking at sum is not minus 1. Okay, you have to be looking at what's this series type. This is obviously a divergent series, right? We can check it out. We can actually figure out what our series is, our a sub n. We can, figure out what our limit is. You can do the nth term test for divergence on this one. If it diverges, my sum's going to probably be infinite, which is not the same thing as minus 1. Okay, plus also it's minus 1. There's all these positive terms. Where did the minus 1 come from? Okay, so be very careful. It's a common mistake people make when they look at it. They go, I'm just going to multiply and it's, make some simple assumption. It's not like that. You have to look at what the series type is because you're working with an infinity of terms. Okay, and I can't just kind of fiddle with the first couple terms and kind of make it work that way. Okay, so that's 5.2, right? We talked about a couple different series types, right? So maybe you have some things you can put into your table already. Or not, you don't have to do the table at all, but take a look at the homework. We can, if we have time, we'll talk about the homework on Wednesday. But the homework for 5.2 is due on Thursday, and also we have a quiz on Thursday on 5.2, okay? Okay, guys, I'm gonna let you go here because we're done with 5.2 and I don't wanna rush it. So have a great day. I'll see you on Wednesday.
Thank you.
Thank you. Have a good one.
Take care.
Thank
Bye-bye.
you.
Thank you.
Thank you, everyone.
Take care.